This meeting is being recorded.
Welcome, everyone. Thank you for coming to our distinguished lecture series for today. We're just giving everybody the opportunity to come on into the virtual room. We'll get started very shortly. Thank you so much. Welcome, welcome. We're excited to have y'all. Welcome. Good afternoon, good morning, wherever time zone you are in. We're about 2 minutes shy of our start time, but we want to give everybody the opportunity that has logged in to join in. It is Wednesday, so happy Wednesday. All right. And while everybody's gathering in, thank you so much for coming. We just want to welcome you to our Distinguished Lecture Series. We're excited to have Dr. Alù here with us. Welcome, welcome. For the question that came into our chat, this will be recorded and it will be issued onto our YouTube page for future viewing. Thank you for that question in advance. We're excited and we are right at the top of the 1 o'clock hour. So I would like to turn this over to Dr. Roach.
Good afternoon, all, and thank you so very much for attending the 6th in a series of distinguished lectures sponsored by the Chief Scientist Office for the Air Force Office of Scientific Research. We're really thrilled and excited to have Professor Alù from CUNY here with us today. I'll hold off there because I'm going to ask Dr. Nachman to do the formal introductions, but I want to give a little shout out to the Distinguished Lecture Series. We started this series with the intent of trying to be able to see some of the most top-notch scientists from around the world within our series that we either fund or we consider to be at the top of their game. And so that goes without saying that every single one of the folks that we've seen so far are some of the best in the world, and certainly Professor Alù's reputation precedes him. With that in mind, to go over the rules of engagement and the logistics, I'm going to turn this back over to Ms. Barner.
Well, again, welcome. We are excited to have you. We will be opening the session. For those that would like to pose a question to be answered, please use the Q&A feature that can be found at your bottom text message, but you could also raise your hand and we can actually pull you up to verbalize during the session as well. And we will determine when the best time it is to review those Q&A. It may be during the talk, it may be at the very end, but please keep your hand raised and we'll be happy or put your question in the Q&A and we will review as such. Thank you so much. And I will turn it over to Dr. Nachman for the introduction.
Great, thank you. Do I have to push my share screen or something?
No,
Click on that?
Nope, you're live, sir.
Oh, okay. Well, hi, those that don't know me, I'm Dr. R.G. Nachman. I manage the electromagnetics portfolio at AFOSR. And today's speaker, Dr. Andrea Alù, is someone I've been funding for a long time. I think starting in 2011, he was a young investigator choice from me, and he's been more or less funded ever since by AFOSR one way or the other. Currently, he's the principal investigator on a MURI, which he runs at his City University Research Center he has there. He's won numerous awards. He's a fellow of several important professional societies, the American Physics Society, the Institute for Electrical and Electronic Engineers. I don't know, I'm missing a bunch. I saw the Optical Society of America, et cetera, and he won an NSF award and many others. In fact, I've spoken about him on several previous spring reviews where I list all of his winnings. He's a Simons Fellow, which is another big award. And so when Dr. Roach asked for nominations from program officers like myself, I didn't hesitate a minute to offer him up, because I think he does very interesting work and is a talented speaker. So I think without further ado, let me turn this over to Dr. Alù rather than me.
Great. Thank you. Thanks, Dr. Nachman, for the kind introduction. Thanks, Dr. Roach and Dr. Barner also for the invitation and for being here. And thank you, everyone, for joining in this presentation. I'm very excited to be featured on this series. I'm very honored. And also, I'm very grateful to the Air Force Office of Scientific Research for the continuous support. As Dr. Nachman said, I've been continuously funded throughout the years since I was an assistant professor. I think my first actually external grant was a small AFRL grant with two research scientists, Dr. Bob Shore and Dr. Artur Yagjan, as kind of supporters through Dr. Nachman. And then over the years, I got the Young Investigator Award, and MURIs have been supported also by Dr. Gerno Pomranki and Dr. Ali Sair. I'm really grateful. And many of the things I'm going to show in this talk are really fruit of this continuous generous support over the years. So today, I want to tell you a bit of a background and history of what we've been doing over the years, thanks to this support in the context of manipulating waves, in particular light and sound, with engineered materials known as metamaterials. The talk will really showcase a few examples of how we can tailor wave phenomena and wave physics with engineered structures. And so my first slide is really to showcase the breadth and generality of wave phenomena all over around us, from light that comes from the sun or from thermal emission or from lasers to sound, thermal fluctuations, mechanical waves, water waves, seismic waves. They're all very different phenomena, very different platforms, but they all obey similar, actually, mathematical rules. And the beauty of this mathematics that drives the physics in so many systems is particularly compelling from the point of view of really curiosity-driven research, as the basic research that AFOSR funds. At the same time, waves address many technologies and many grand societal challenges for today's world, from wireless communications to computing, to sensing, to imaging, to energy harvesting. All of these today rely strongly and fundamentally on wave physics and on how waves interact with materials. So the role of our research is really to explore ways in which we can challenge first the fundamental assumptions about wave physics and wave matter interactions, and also propose ways of using these new interactions to drive technologies that can be of benefit to the Air Force, to the Department of Defense, and more generally to society at large across all these domains of applications. What is quite interesting is that despite the fact that we have such a breadth of wave physics, actually the materials that we use in tackling these waves in many of our devices and the ubiquitous role that they have in tailoring waves are actually based on a quite limited set of materials. And all of these typically are hindered by weak wave matter interactions that imply that the materials either have to be bulky, the devices that are made of these materials have to be bulky, or they have limited efficiencies, limited ways of interacting with the waves and limited performance metrics. And in this context, in the past 2 decades, a new palette of engineered materials has been introduced. And these materials, known as metamaterials, have been pushing the boundaries of wave-matter interactions that can be associated with sound, with light, with radio waves, and many other forms of wave phenomena. As you see in these pictures, metamaterials are engineered materials at the nanoscale or the deeply subwavelength scale that can be treated as bulk media in the way in which we then form devices out of these materials, but at the same time, they offer properties that are very different from what nature offers us and from the constituent elements that make these materials up. So typically, we use quite common materials as the basis. In fact, we like to rely on materials that are compatible with existing technologies like silicon-based structures, but at the same time, the arrangement, density, orientation, shape, geometry of these engineered structures lead to emerging properties in the way they interact with light, sound, radio waves, and other waves in unusual, exotic, and non-existent way in nature. I don't have time to show you all the breadth of what metamaterials can do, but I will pick a few examples. And the bottom line is that they can fit in our devices. They can lead to more efficient communications, to better cameras for our cell phones, and to many other opportunities for pushing forward science and technology. So if you're not familiar with this topic, I want to start from something very basic that is actually the core of where metamaterials started, and then dive into the more recent developments. So arguably, the most common phenomenon for light, for optics, is the phenomenon of refraction. The law that governs the refraction is Snell's law that has been written down well before actually Maxwell's equations were discovered, and basically governs the way in which light is bent when it enters a material with a different constituents, with a different index of refraction, n. Typically, the larger is the index of refraction, basically the density of polarizable matter of our material, the more the light rays bend towards the normal to the interface. And this phenomenon is ubiquitous, and actually is at the basis of many of the devices that I will show you across my talk. Really, what we deal is the interaction of waves to interfaces, and to interfaces showing a large contrast between indices of refraction. But fundamentally, this is actually the response of many atoms, molecules, polarizable particles that are driven by electric and magnetic fields. And as a collective array of these minuscule elements, we can describe the material with an effective index of refraction n that governs the macroscopic way in which light is bent as it enters the material. The effect that we actually see is that, for instance, a straw of light is broken if we immerse it in a glass of water, because of the contrast in index of refraction. So this is a typical refraction phenomenon. About 5 or 6 decades ago, Victor Beselago, a Russian scientist, asked the question, what happens if I would discover a material that has actually a negative index of refraction? And simply using arguments based on Snell's laws and boundary conditions at this interface, he discovered that a beam of light entering this material would actually bend negative. And since then, there has been a lot of interest in trying to discover these materials. At first, Beselago and other colleagues in material science were trying to find in nature such a material, maybe in a narrow range of frequencies. But about 2 decades ago, was discovered that we can actually engineer our materials to realize an effective negative index of refraction and bend light in this unusual way. This, as a macroscopic effect, would lead to something like this, as you see, a much more striking optical effect. This, by the way, was produced just with Photoshop, because we do not have a broadband liquid form of negative index material in the visible to do this in an experiment, but still it shows how this type of negative index materials that have been produced in many different range of frequencies can provide quite striking optical effects. And in fact, over the years, there has been proposals, including proposal that I developed back when I was a graduate student with Professor Nederengeta at the University of Pennsylvania, to use this to actually hide objects or manipulate the scattering of objects from external observers. The idea is that we see objects through actually scattering from their surfaces, from the same type of impedance mismatch interfaces that drive refraction and reflection phenomena. And the question is, can we eliminate this scattering by coating this object with a suitably tailored metamaterial that can somehow scatter light in a way that it interferes destructively at all angles with the scattered light from the object in a way that it can conceal the object and making effectively transparent. This has driven a lot of initial interest in this field. And now, of course, the field has evolved. I will show you in a moment that actually there are some fundamental limitations as to how broadband and how effective this phenomenon can be. But it's also interesting, of course, this has driven the initial excitement was around potential applications in concealing large objects. But for the moment, the most successful demonstrations have been the ones targeting longer wavelengths and smaller objects for applications, for instance, for radar camouflaging. This is an example that we worked out a few years ago at the University of Texas at Austin, where I was working as a faculty for 9 years, and in which we coated this ceramic-based metamaterial. We used it to coat a dielectric cylinder, demonstrating about 20 dB scattering suppression in the radio frequency range. This is how the waves interact with this complex metamaterial. It's interesting that each of the elements of the metamaterial is actually a large scatterer, but the orientation and the arrangement of these structures around the object make an effective medium with a negative permittivity that can actually cancel the scattering from the core. And interestingly, all the scattering from each element of this metamaterial come together to realize this effect of transparency as a whole. That is quite striking, because it doesn't is not limited just to far field or to specific directions or specific excitations, but it actually applies to arbitrary excitations, arbitrary observations, even in the near field, even at the back of the object. Now, over the years, we have developed applications also working with DoD labs and companies for products like this. This is a radio transparent antenna that offers a much reduced radar cross-section, and yet it can transmit and receive over a quite broad range of frequencies, again in the millimeter wave LTE. This was designed for the LTE range, and it can also be dual polarized. Another quite striking example is these struts that are can be useful as mechanical support, but can be made radio transparent to even in the near field of an antenna. So these are two experiments in which we have a horn antenna sending a radio wave that hits 3 metallic struts, and then we cover them with metasurfaces, as we call them. These are basically very thin metamaterials that can be wrapped around the object conformally. And indeed, in the measurements, you see how the problem with the metallic struts is largely affects the radiation. In the center, you see the radiation from the cloaked struts that can be arbitrarily placed, by the way, in front of the horn. And this is actually the reference measurement if we remove completely the struts. So you see that these layers around the metallic objects can really suppress drastically the scattering signature of these structures. going to optics, and here you will see over and over in my talk how we can actually translate these concepts from wide range of frequencies, range of applications and functionalities. This is work we've been pursuing also in collaboration with Kuipers in the Netherlands, in which we demonstrated how this concept can be applied to a near field scanning optical microscope tip. And by properly engineering the tip to realize this same concept of a negative effective polarizability for the element, we can improve the measurement of this microscope. We can make the microscope tip less affecting its own measurement, and therefore avoid the tuning of the tip and enhance the fidelity of the imaging functionality of this sensor. At the same time, support from the Air Force over the years has also led us to study the fundamental limits. And it's interesting that you can develop actually quite general bounds on what you can do with this type of techniques, and realize that there are trade-offs, that not everything is so rosy as was originally expected at the beginning of this field. Sometimes research into actually investigating the nature of this phenomena helps us really understand where are the bounds and what we can do with it. So you will notice that both of the applications I showed you are limited to objects that are comparable to the wavelength of excitation. So for a radio wave, this is in the range of tens of centimeters, like an antenna or a strut. But for optics, we are limited to these microscope tips that are very tiny objects, because the wavelength of light also shrinks. So in general, one can prove, and I don't want to show you large equations, but we found a general formulation for the trade-off between the maximum scattering cross-section reduction that can be achieved by a passive metamaterial coating, the bandwidth over which this can be achieved, and the size of the object compared to the central wavelength of excitation. So over the years, there have been several types of cloaking technologies developed, but as long as they are passive, linear, and time invariant, all of these must obey this general bound in which we trade scattering reduction with bandwidth. And this actually can guide the design of these structures and the type of applications that we can target. We have also an interest in active type of metamaterials that can overcome some of these bounds. And this is actually applies not just to cloaking, but to a broad range of technologies in which metamaterials can push the boundaries of wave physics, but also have to face trade-offs. Active structures providing energy to the wave as it interacts with the materials can somehow push some of these boundaries a bit further, but still complying with physical limitations. And by the way, just as a curiosity, we have applied these formulas to envision what is the maximum bandwidth over which one could cloak in the visible or hide in the visible a human scale type of object. And it follows from this formulation that as long as you stick with passive linear time invariant coatings, and assume, for instance, a central wavelength in the visible, in the green light, that you have a very stringent bound on what you can do as a function of the scattering reduction here in logarithmic scale, in dB, over which that determines the bandwidth over which you can actually suppress this scattering. You see that basically the promises sometimes you still see on the news about how one can build a broadband cloaking device may have to face fundamental constraints on the physics of this problem and the challenges that this may face. Yet metamaterials have flourished in many other applications. By the way, one curiosity is that dual to this idea of canceling the scattering, there is also the opportunity to make a small object look much larger than it is. And this is actually quite exciting for sensing applications. We've been working actually recently, since I have started working here at the City University of New York Advanced Science Research Center, with our colleagues in the same building that work on neuroscience or biomedical devices, that the idea of using tiny nanoparticles that can have a cross-section much larger than their physical cross-section. And this can be used for to enhance the imaging of biomedical for biomedical applications. Another exciting prospect of metamaterials has been the idea of realizing metasurfaces. I already mentioned a bit the idea metasurfaces are ultra-thin metamaterials that basically are planarized, have one dimension that is much smaller than the wavelength. And the vision around this technology is that it can actually largely shrink the footprint of complex optical technologies. We are used to lenses, to polarizers, to diffraction elements like holographic displays. They all typically take many wavelengths of light to realize complex functions. And the idea of metasurfaces is that we can engineer an interface at the nanoscale to largely modify the impinging spectrum and imprint a pattern of choice, essentially pixel by pixel, point by point, between input and output on the input wavefront. The usual approach to tackle this type of devices is to engineer this structure at the nanoscale, giving very powerful spatial control over light at the nanoscale, but typically poor spectral control. Typically different wavelengths, here sketched with different wavelengths, are tailored with a similar waveform, but with some distortions that depend on the frequency dispersion of the different elements of this interface. So in the last couple of years, we've been very excited to explore the option of engineering these metasurfaces at a global scale. We call them non-local metasurfaces, and actually several groups are now pursuing this type of approaches and actually take full advantage of this global engineering of the output wavefront, as I wrote it here schematically as an integral over the space of the input wavefront. This allows you to get full control over the input wavefront in terms of bandwidth, so spectral control, frequency response of polarization, and of the spatial features that you imprint on the object. So you can create, for instance, a metasurface that is completely transparent over a broad range of frequencies, and then targets a specific wavelengths and patterns this wavelength arbitrarily at will. It opens up a lot more degrees of freedom in the design of these ultra-thin optical devices. And I will show a few examples of this. First example is this radio frequency platform. This is operated at millimeter waves for 5G type of wireless communication technologies. These surfaces, each of them is very subwavelength. Even the stack is still very subwavelength compared to the wavelength, but yet each of them is transparent to each other, and therefore we can engineer different functionalities for each surface. For instance, this stack was designed such that a broad range of frequencies go through unperturbed, completely transparent, but selected frequencies can do selected operations. The first surface, for instance, tackles the green wavelength, 18.5 gigahertz, for right-handed polarization and focuses it. The second surface can address a different wavelength for the same circular polarization, but steers it instead of focusing it. And the third surface instead tackles the first frequency as the previous one, but for the opposite polarization, and steers it to the opposite side. These are measurements confirming this response, really providing the agility that one needs in the context of reconfigurable intelligent surfaces, this growing emerging field of wireless communications that addresses the growing demand for data rates and for many users connected at the same time across the same spot. These concepts applied to optics can also lead to very exciting devices in the context of augmented reality. For instance, we can look through a metasurface and see the background, but at the same time project on the metasurface and towards the eye specific information with color, for instance, with 3 colors, still maintaining an overall transparency for the other colors involved. And this type of efforts, I don't have time to show you all the devices we built, but we're happy to see that they're evolving fast also into transition with collaborations with AFRL. For instance, this is work we're developing with Dr. Tuma at the Kilby Directorate, Munitions Directorate, with a new program on non-local long wavelength infrared meta lenses that are transparent across a wide range of frequencies, but have selected wavelengths in which they focus long wavelengths, and an SBIR program on the wide field of view multi-wavelength meta lens, again applying the same approach, but now into the optical regime. Another way of using this type of engineering of the optical wavefront or the electromagnetic wavefront is the one of realizing analog computing. You are familiar with how our computers work. We typically process signals in the digital domain that requires actually as a bottleneck in terms of speeds and in terms of energy efficiency of this challenge. In fact, I've led in the past a MURI program on supported by Dr. Geno von Ranke and Dr. Arjun Nachman on the attojoule optoelectronics, being able to slash down the energy demand of optoelectronic systems in terms of computing. And one of the byproducts of this program has been the realization that we can actually use wave physics and metamaterials to process signals directly in the analog domain at the speed of light, as light interacts with these metamaterials or metasurfaces, exploiting non-locality engineering. So the idea is to build a metamaterial that can, for instance, apply a mathematical operation on an object and transform an arbitrary signal into its derivative or its integral or its arbitrary linear operation on the material. For instance, a good application for that is the idea of realizing edge detection, having an image, an arbitrary image, ideally dual polarized with arbitrary edge orientations that and have a very thin film that just placed in between the object and the camera can let through only the edges, whatever they are, of the object. This is actually particularly important in the context of self-autonomous driving and object recognition, because feeding a complex image to a computer makes quite difficult to detect the individual elements. Typically, a computer has to do this form of edge enhancement in the digital domain, but we can relieve some of this processing and do it in the analog domain without energy consumption at the speed of light by using this form of thin films that exploit non-locality engineering on the surface. This is a schematics of what the digital image processing type of chain would do. It's clearly intensive in terms of energy and has a bottleneck in terms of speed. However, this is a recently realized optical metasurface that works for dual polarization, has close to maximum efficiency for a passive device to do edge detection, and can also operate over broader bandwidths than typically expected for this type of devices. And essentially, it's a very thin film, about 100 nanometers in thickness, that you can place anywhere between the target and the metasurface and the objective, and essentially lets through only the edges of an image, in this case, the logo. These are different experiments done by moving the surface, actually, between the objective and the target. And indeed, you see how the, I mean, as you put it very close to the objective, there are issues with near-field coupling between the optics. But other than that, you see the response is actually independent of the position of the metasurface. Another advantage of this design is that if you place a polarizer before the image, basically you illuminate with polarized light. As you rotate the polarizer, you can actually enhance specific edges that can be of interest for polarization imaging. This is another exciting direction to enhance the visibility and the detection of complex images and recognize objects that may be hidden in a complex background. We can do even more than that. If you actually add feedback to the system, you can realize an effective form of optical computing. You can actually solve a complex mathematical operation in which you have an input, and your output is the solution of a complex mathematical problem. This problem here is an example, is an integral equation in which the output function g is both outside and inside this integral. And we built in collaboration with Albert Polman and Nader Engeta a metasurface that can do that. This is actually the nanostructured device, has a feedback introduced by a second interface on top of the surface. And by interrogating it through multiple diffraction orders and waiting a few optical cycles, still a very short amount of time, the output of this metasurface is the solution to the problem of interest, the mathematical problem. For now, of course, this system is stuck to solve a specific mathematical problem that for several applications may be very well fit, but one exciting opportunity as we go forward is to think of ways to reconfigure or reprogram this type of platforms to realize something closer to an actual computer in which we can also program the response. But I want to stress also here, by interrogating with different inputs, we can get at the speed of light with essentially zero energy requirements, the solution of a complex mathematical problem. We've also generalized this, and for now this is just theory, but we're actually working on an experiment in silicon photonics we've shown how this can be generalized to actually a nanostructure, a structure that is sub-wavelength in size, and by interrogating it from multiple angles or with a complex incoming wave and looking at the scattering from this wave, it's possible to realize a nanoscale form of analog optical computing that solves a complex mathematical problem at the speed of light. Another target of our investigation has been to apply these concepts of metasurfaces and optical manipulation to thermal light. So far what I showed you requires that the excitation comes from a laser, from a coherent form of excitation, but actually the most common and widespread and cheap form of light is actually thermal emission. It comes from the sun, it comes from incandescent objects, it comes from all hot bodies around us, including, we're very familiar in the context of defense application with the night vision goggles that try to pick up the thermal emission from hot bodies in the context of night vision. Thermal emission is notoriously incoherent and very broad band, so it's difficult to tame. And there has been a lot of efforts in the past 20 years on manipulating its features by using, for instance, gratings. The seminal work of Jean-Jacques Greffet, for instance, in using gratings on special materials like silicon carbide that offer strong phonon resonances, allow you to tailor this emission and make it more directive and more narrow band. What we've shown is that, and this, by the way, is work supported for the most part by our Van Nevar Bush Faculty Fellowship from DOD, is the idea of applying these metasurfaces to thermal emission and really open up the floor for all these degrees of freedom that come from nanoscale engineering of a structure to manipulate the features of thermal light. And also this applies to photoluminescence, basically to light emission diodes that also are forms of incoherent broadband emitters. This is an experiment showcasing a thermal metasurface that is geared to show narrow band. This quality factor here is about 100. So the fractional bandwidth is about 1/100. And that emits mostly into circular polarized light and at an angle from the surface. So imagine a passive surface, and what is surprising, this is just silicon. We don't use any special material, any material resonance to engage with thermal phenomena. It's really driven by these optical states that are engineered through non-local interactions across the surface. And this, as you heat it up, provides a form of incandescent emission that is very narrow band, very directive, very polarized to a specific angle, a specific polarization. These are all experimental results, different metasurfaces that showcase how we can actually select arbitrary polarization of thermal emission from basically hot bodies as we heat them up and we tailor the specific wavelength range of interest. This is in the mid-infrared, in around 4 micron wavelength regime. So these operate in the range of 100 Celsius or so. You can pattern this arbitrarily, so you can create, for instance, a focusing from an aperture. So this thermal light, as you heat up the surface, can be focused at a specific point in space. You can use this basically as quasi-coherent sources of light that come essentially for free, just from heat. And this one is a more sophisticated design for now, just a theoretical and numerical simulation demonstrating a thermal emission with a tailored angular momentum, both in terms of spin, of the spin polarization, and in terms of orbital angular momentum of light that can encode information through this emission. And this, what is remarkable is that clearly this type of emission patterns, as several of the others I showed you before, have intrinsic forms of momentum emitted through the surface as you heat it up. That implies that the surface itself feels a back action. It actually would experience a force as it emits light and thermal light through thermal emission. I don't have time to show you the implications that metasurfaces have also to manipulate nanoscale light. We've been working quite extensively on applying these concepts for with a bit more special materials that support their own material resonances. We call these polaritonic metasurfaces. Polaritons are these quasi-particles that come from the strong coupling between light and matter responses in a way that you cannot distinguish anymore what is vibrating, if it's light or matter, or it's really the combination of the two. And these have shown extreme manipulation of light at the nanoscale, giant nonlinearities for applications in limiting harmonic generation, down conversion, up conversion, and also quantum phenomena, unveiling really quantum platform for optical and radio wave applications. But what I do want to show in the last few minutes of my talk is the possibilities that are opened by introducing the temporal modulations to the metamaterial response. And we've been working on this for several years now, in particular in the context of the MURI that now is in the last year of support. Very successful MURI, I would say, in which we have demonstrated how time modulation can break one of the fundamental symmetries in wave propagation that apply to a wide range of technologies, a wide range of material platforms. This symmetry is known as time reversal symmetry, as reciprocity. Is the idea that if we have a channel of transmission from point A to B in an arbitrarily complex medium, there typically is a reverse channel that transmits back with the same strength from point B to point A. This is actually useful in many circumstances, but also can create challenges in a wide range of technologies of relevance to all of us, including in the context of isolation, of laser protection, for instance, or source protection, of circulation, in the context of wireless communications, full duplex transmission, the efficient use of the scarce spectrum, electromagnetic spectrum, and for radar applications, and also in the emerging field of quantum computing, of nanophotonic computing, in which we have a one-way stream of data that has to be integrated in a compact platform. In all these type of applications, the available way of breaking reciprocity and realize this one-way form of transmission, avoiding back reflections or rerouting to different sections of our circuit, is to use magnetic bias. So we can break the symmetry I was talking about, but typically using magneto-optical phenomena that imply large footprint devices and difficulty in integration. For this reason, there has been, by the way, another challenge is that this type of magneto-optical materials typically come from regions of the world that are not necessarily the easiest to get access to materials, and there is a large interest in trying to realize technologies that mimic magneto-optical responses without the need for rare earth materials. Indeed, in our research, we've been exploring ways to break non-reciprocity using metamaterials, in which the metamaterials are combined with other forms of bias that typically are also quite weak in their impact on waves, but can be largely enhanced when using metamaterials to boost this asymmetry. We've been using moving media, time modulations, and nonlinearities to break the symmetry in transmission and realize non-reciprocal technologies. Our first work on this concept actually applied to sound rather than to radio waves or light, simply because sound is slower and in some ways easier to tame. So we showed this tabletop experiment in which by using 3 fans, small fans that move air in a tailored acoustic cavity, it was possible to route sound from one port to the one on the left and isolate the one on the right. You will notice how geometrically this cavity is completely symmetric. So the only reason why sound chooses to go to the left instead of the right is that actually there is a flow of air, a slow flow of air, much slower than the velocity of sound, that actually circulates in the opposite direction. This induces Doppler shift that can be combined with the resonance of the cavity to route sound non-reciprocally. And when you feed the second part, the sound will go to the third, from the third back to the first. So this choice, this handedness is really at the basis of this non-reciprocity and circulation of acoustic waves that we're exploring its use in acoustics, for instance, in the context of enhanced ultrasound imaging or for sonar applications. Yet there are a lot more ready available applications if you look at the electromagnetic spectrum. But as I said, light is a lot more difficult to tame because of the speed. So instead of mechanically rotating or moving media in the electromagnetic context, we have chosen to look at a synthetic form of motion, of angular momentum, that comes from modulating in time the response of these structures. So we typically start from a symmetric, circularly symmetric cavity that supports degenerate resonances, left-handed and right-handed. For symmetry, they are identical. We then pattern spatially a modulation in space of the response. This cannot break reciprocity, even if you make it asymmetric, because of the time reversal symmetry I described a few slides ago. But then we can modulate in time each of these segments with different phases. And that choice of phase can actually break time reversal symmetry, can apply an angular momentum bias to the system that is not mechanical. It's actually stems from time modulation. And this can realize integrated devices in which we can modulate weakly. As I showed for sound, we don't need to chase the velocity of light. We can modulate with small amplitudes, with small frequencies as well, the structures, and yet realize large isolation on chip. The most successful transitions of these have been in the context of radio frequencies, because we have a lot of very powerful devices to modulate strongly our devices, and also because radio frequencies are simply slower in time. So it's easier to realize broadband phenomena in terms of non-reciprocity. These are a series of devices that we've been realizing over the years integrated fashion, non-reciprocal antennas, and printed circuit implementations. This one, the center actually uses micro electromechanical switches to realize very low power consumption circulators for radio frequency devices. And also in this framework, there have been several opportunities for transition in the context of collaborations with the DoD labs for the Air Force, Navy, and the Army. We have 2 Lucy programs and a new BAA tailored actually to look at high frequencies for these concepts, and also an SBIR program that now is in the option period of the phase 1 that actually aims really at pushing the commercialization of some of these devices for millimeter wave applications in collaboration with Silicon Audio. These concepts are not limited to guided waves. Of course, guided waves have a broad impact because they can be applied to radar technologies, to automotive, and also pushed to the optical domain. But another broad range of technologies that suffer in some ways from reciprocal responses are antennas. Antennas have to transmit and receive with the same features. This is kind of electromagnetics 101. We don't even measure reception patterns of an antenna because we trust reciprocity that the transmission pattern will be identical to the reception. But this also implies that if I try to create a broad angle radiation, the antenna is also prone to jamming from different angles. And the implication of this is also important in the context of energy harvesting. If I have a good absorber, this must be also an effective thermal emitter towards the same angle at the same wavelength. And this implies that there is a fundamental bottleneck as to how much I can actually absorb from a body that becomes hot because of absorbing energy. Non-reciprocity allows to have antennas that do not need to be jammed, and absorbers that can thermally emit somewhere else rather than emit back towards the source, so that you can recycle the energy. And indeed, we have demonstrated this proof of concept a few years ago. Again, we exploit time modulations. This is the type of antenna we use. This is a leaky wave form of antenna that is modulated in time through varactors. And indeed, as we turn on a modulation signal, that is actually interestingly fed through the port with which we fed the antenna with a regular signal, but it's a low frequency modulation signal. We can bias the antenna, break time reversal symmetry, and realize efficient radiation outward, but no reception of the signals at the same port. And speaking of time interfaces, the last couple of minutes of my talk, I want to show you how this concept of spatial interfaces that can build metamaterials can be enriched by the use of time. I already showed you how time modulation can break a fundamental property of light, but I want to show you now that is reciprocity, but I want to show you now how we can use this temporal dimension to introduce new forms of interfaces to the interaction of waves with matter. So this chart shows a schematic of the reflection and transmission through a one-dimensional interface. So the spatial dimension is the horizontal axis, the vertical dimension is time, actually. So a wave that travels in one dimension has an angle that depends on its velocity. As it hits an interface in which the permittivity or the index of refraction changes, it's partially reflected, partially transmitted. And multiple of these reflections build up a resonance. That's what is at the basis of many of the devices I showed you. Can you now think of a time interface in which the wave does not experience a discontinuity in space, but it's actually discontinuity in time? So the entire medium, or at least the portion of the medium that contains my signal, is abruptly and uniformly switched in time to a new material. What happens to the wave? Interestingly, these problems are dual to each other. In the first case, we rely on the fact that frequency and energy are conserved, but the momentum changes. The wave is reflected back because of momentum change. At the time interface, momentum must be conserved because of translational invariance of my switching event. But frequency and energy can change. And this can lead to reflections because we can couple two negative frequencies. It's the dual of the negative momentum we see in a reflected wave in space. Here, the wave can be reflected back, but it's time reversed because we couple two negative frequencies, provided that the interface has a sufficiently strong impedance mismatch. And the first demonstration of this type of phenomenon was shown in the context of water waves by Matthias Fink in about 6 years ago, by basically, in a swimming pool, basically having a kick of the interface. He showed he could time reverse an image that was being diffracted out in time would come back to the source and form again. So you see already that this kick produced a broadband phase conjugation of a signal that actually for water waves has arguably limited applications. It's just an impressive and neat experiment, but for electromagnetic waves have huge implications for radar technologies, for channel estimation, so for a broad range of wireless communication devices. So we've recently been able to demonstrate the first photonic time interface in which really electromagnetic waves get time reversed. We used this 6 meter long meandered transmission line in which we can switch on and off reservoir capacitors that can create that form of abrupt change of impedance that creates phase conjugation, broadband, instantaneous phase conjugation, and frequency translation, by the way, in a compact in this form of compact in time, I would say, structure. So I want to stress again, the spatial reflection has basically a first in, first out type of response. It's like an echo, but it's a temporal echo. So it's a first in, last out. You time reverse the entire signal, however broadband it can be, with an abrupt change in time of the response of the structure. And actually we measure this, we can see this form of broadband frequency translation. You see the frequency translation in this stretching in time of the signal. This broadband signal is stretched in time and this time reversed as we receive it at the input port. And these are measurements demonstrating this response over a broad range of frequencies. This works in the megahertz range. We have now we're now working on an extension that would work up to tens of gigahertz in a CMOS circuit. We can also combine multiple time interfaces to build a form of resonance in time rather than in space. So the dual of a building block of a metamaterial, and we have also observed this form of Fabry-Perot resonances in time rather than in space. We're very excited about these results. Are really the building blocks for new technologies. We're envisioning this type of wireless metasurfaces that can exploit this ultra broadband instantaneous phase conjugation and frequency translation, very efficient without need for digital or buffer type of responses. And in general, we are envisioning this form of Floquet metamaterials in which we exploit the space and time interfaces together to realize a new photonic, acoustic, and elastic responses in a wide range of technologies. So my bottom line of message of this talk is this breaking waves with metamaterials that have has a really broad range of implications of platforms and of technologies that can be applied to really curiosity driven, but with a rich plethora of opportunities. I've recently written a kind of overview article of this field. If you're interested in, appeared in Scientific American. If you speak Italian, was just translated this month also in the Italian version of Scientific American. And I want to acknowledge, of course, my group member, and in particular the FOSR, for the continuous strong support that has really enabled the research I showed and all the excitement around these latest results. Thank you.
Thank you, Dr. Alù. There's seems to be 11 messages in the chat room. I don't know if you can see any of them.
Yes.
There's
Yes.
actually one Q&A that is actually written, and that's from Stephen Array. The question is, could this new technology use all wave matter rather than just the sun to generate electricity?
That's a great question. Actually, Dr. Nachman asked me this question as well, and it is an interesting direction to try to exploit actually waves all around us to generate or harvest energy. There are already some examples of this, especially in crowded environments in which there is already a lot of waves, wireless emitters around us. And of course, enhancing energy harvesting capabilities can allow us to get more and more out of the energy that is oscillating around us without even us realizing. So definitely, this is a very exciting direction that should be pursued, and metamaterials can play a big role in that.
Just as a reminder for those that are wanting to ask questions, please use the Q&A feature versus the chat. And we have 3 open questions. And if there's anybody that wants to raise their hand to ask their question verbally to our speaker, I'll be happy to pull you up to that. Just give me one moment. I see a hand coming up. Okay, did come up. But in the meantime, sir,
so I can read, by the way, some of these questions.
okay, go ahead, sir.
Arthur, thank you, by the way, for all these great questions. The first question is, for analog computing, can you implement an affine transformation with nonlinear activation function using a metasurface? Excellent question, by the way. We are working in that direction. So far, this analog optical computing and signal processing has been limited to linear operations because of the weak, typically weak interactions of light with nanoscale structures. But in other programs, we have been looking at ways of enhancing these nonlinearities, and we do have an interest in implementing. In fact, we have some initial preliminary results that look quite promising in the context of a MURI program, actually, that started last year. That has one of the goals is in also funded by FOSR, by the way, from Dr. Gano Pomeranki, in which the MURI is led by the Duke University, by Dr. Megan Mikkelsen. We have been exploring ways of enhancing the nonlinear aspects of this optical computing, and it's certainly it would be the most exciting opportunity, right, for many applications to add nonlinearities to this type of operations. It's certainly possible.
Wonderful. We are right at the 2 o'clock hour. I would like to give one more question before we end. And we do have someone that did raise their hand. And then also we could also follow up with these questions post-event to answer them, if that's something that would be of interest to all. So I'm going to allow the person that's in our chat to ask. So I'm pressing the allow for the, if you unmute yourself, sir. And I'm gonna mispronounce your name. Moussaoui, Moussakandji. If you unmute, you can ask your question. All right, well, we will.
Well, there is a question from Rebecca Savio, which is interesting. And she says, for your active material meandering waveguide, are you using non-Foster circuits?
Excellent question. By the way, for who is not familiar, non-Foster circuits are active circuits that connect actually very nicely with what I was saying about clocking and the need for active devices to break some fundamental limitations on the bandwidth trade-offs with the interactions of waves. In this specific realization, we've actually been using just switches and passive capacitors used as reservoirs. But actually, non-Foster elements added and subtracted from the transmission line would add very interesting opportunities for doing things that actually may be a lot more sophisticated than just phase conjugation. So we've been exploring this theoretically for now, this opportunity. Of course, as you know, non-Foster elements add complexity and they may incur in instabilities, but it is a very exciting direction to explore. We are not just for this, we're also working on ways of using this type of temporal modulations and non-Foster effects coming from these temporal modulations for beating some of the bounds on electromagnetic radiation for electrically small antennas. That is a topic I didn't have time to discuss in this talk, but it is indeed very relevant, especially for DoD operations in which we need to transmit low frequency signals with efficiency. But certainly it's a very exciting topic, especially the combination of these non-Foster technologies with metamaterials, metasurfaces, and more sophisticated electromagnetic engineering.
Thank you, Dr. Alù. I want to be honorable with everybody's time. It is now 2:03, and again, want to thank you for your talk. And again, we will follow up with those that have questions and send that out to the audience so everybody can hear. Yes.
Yeah, feel free to reach out. I'm happy to stay longer or to answer later at any time. Thank you for all the interest.
We are starting to get people to drop off. So again, just want to be honorable in everybody's time. And that way we can answer those. I'll get those questions to you, Dr. Alù, and we can get those answered for everybody. And that way it is still a very interactive discussion. Thank you all. I appreciate everyone coming, and have a great afternoon, everyone, or good evening and good morning, wherever you are.
Thank you, everyone. And again, thank you, the Air Force and Dr. Nachman.
Thank you, Andrea.
Bye-bye.
Bye-bye. Okay, I'm off.